Hello, everyone, and I welcome you all. Thanks for joining this session today. And good morning, good afternoon, and good evening to you from wherever you are joining in. In this talk, I'll talk about four types of real-time analytics systems that you can see today in the analytics domain. When it comes to real-time analytics, it's all about extracting meaningful insight from uh, moving data. And the thing is, not all real-time analytics systems are made equal. They have their differences in the way they operate. So the goal of this session today is to classify these real-time analytics systems into four categories based on five different criteria. So the takeaway for you is the ability to uh, identify and the best real-time analytics database for your next real-time analytics use case. All right, and let's before that, let me introduce myself. Robert gave me a good introduction, but in terms of few additional information, so I'm a senior developer advocate from Red Panda Data. For those who are new to Red Panda or haven't heard about it, it's a streaming data platform API compatible with Apache Kafka. So in other words, it's a drop-in replacement for Apache Kafka workloads. And in the context of real-time analytics systems, it can be used as an upstream streaming data source for your real-time workloads, as well as downstream data sync. And if you have any feedback, any question, or any data-related question in general, you can always find me on these social channels, Twitter, LinkedIn, and Medium. You can also read my blogs on Medium as well. All right, let's get started. And then before we kick things off, I'd like to inform you about Red Panda University. If you are interested in learning more about Red Panda and streaming data in general and stream processing technologies, Red Panda University is a good place to check out some free self-paced online learning material. So I highly encourage you to visit there and check that out. And then also you get a free copy of this state of streaming data report by scanning this QR code. In this report, you will see many of the real-time database products I discussed today in this talk is getting compared in this report with actual statistics. So it's a good place to read once you are done with this talk. All right, let's get started. So what is real-time analytics? Like I mentioned in the beginning, it's the practice of deriving meaningful and actionable insights from moving data. So when I say moving data, the data set is unbounded and it consists of streams of data. There's no beginning or end. So these real-time analytics systems work by uh, ingesting data and deriving insights as the data is ingested. So this is contrast from traditional batch systems we do in the classical days where we store data first and periodically run analytics jobs on that later. And then when you look at the real-time analytics market today, you can see different types of databases and frameworks and etc. I would say the spectrum is vivid and there are so many choices to choose from. So if you are a beginner, you might get lost what to pick from. So, I mean, for example, we have time series databases, and then we have real-time OLAP databases, stateful stream processes like Flink, and then we have data lakehouse platforms, query engines, full text engines, and new kids in the block streaming databases as well. So there are a lot of choices. But the thing is, not all real-time analytics systems are designed to be equal. So there are subtle differences in the way they operate. So, and then this poses you the question. For example, if you are a data professional and if you are beginning a new real-time analytics problem or project, you might get this problem. What is the ideal real-time analytics database I should use for my use case? So that's the million-dollar question we are trying to solve today. in order to make that decision easier, let's define 5 characteristics to classify them into 4 buckets. And then based on these properties or characteristics, we can score them and we can finally pick the ideal product. So there are 5 categories. The first one is the query latency. So this is pretty much common in all real-time analytics databases, and this means how fast this system can generate insights. This latency can be a decisive factor when you are building a real-time analytics system, because some systems have stringent latency SLAs, which are it falls under millisecond range, sub-second range, and some can tolerate latency up to few seconds or few minutes. So it's a decisive factor. And the freshness of data also matters, because when you are making decisions, you need to make sure that your decisions are made on the latest state of data, and it should not be inaccurate, or the decision made on stale data might lead to some disasters. So this means how fresh the insights you are generating. For example, for certain use cases, we need data freshness within few seconds. And for some use cases, it could be up to a few minutes. So we can tolerate delayed data as well. And then third one is complexity of queries. That means how complicated queries we can throw at the database. For example, some databases like key value databases, they have been designed in the mind to support faster lookups by primary keys or some kind of a unique key. But for example, you cannot use key value stores to answer queries with like multiple joins and aggregations and some different projections with multidimensional field. So you need to pick the right database to do that. So this is another decisive factor as well. And then the concurrency. That means, in other words, this could be defined as a throughput. How many queries that this system can answer or serve at a time. So this comes as a critical factor when you think about the audience or the end consumers of your real-time analytics system. For example, some systems can be consumed by internal teams like operational and analytics team, while some systems needs to be exposed to your end users or could be exposed to end users. So there can be high concurrencies in that case. So the underlying database must be able to support this kind of concurrent query throughput. And then final thing would be access to historical data. That means how much of past data you need to generate insights. This is also an important factor because certain applications, certain real-time systems can trigger certain actions based on maybe single event or few events that it has seen in the past few seconds, while other systems need at least few days worth of data to generate more accurate data. When we consider that kind of systems, the more data you have, the more accurate your results get. So this is also another decisive factor. And then if you consider all these factors, 5 factors, think of them as sliders in a audio mix or in a equalizer. So when you have a new real-time use case, you should have presets in these sliders. So that's what we need to do next. Based on different values for these sliders, or I would say different dimensions or characteristics, we can define 4 categories of a real-time analytics system. Excuse me. So there are like 4 major buckets we can define, but keep that in mind. These are not clear-cut, siloed divisions or categorizations. So there can be overlap between these two. So just keep that in mind. And also, when I talk about that equalizer analogy, so for each use case, for each category here, they can have different preset templates of these sliders. So let's have a look at our first one. The first category is real-time automated decision-making system. So basically, this is where we get to see machines making quick decisions without human intervention. So these systems have been designed in the mind to ingest high velocity, high throughput data streams, compute metrics, detect patterns, and react to them by triggering event-driven automated workflows. Latency is a critical factor here, especially low latency. We talk about millisecond latency ranges here. So because of that latency window, there's no human in the loop. That means humans obviously can't make decisions within that fast time intervals. When we talk about different examples for this category, so we can see pattern matching applications like complex event processing systems, so they can detect patterns in incoming data and take action. For example, anomaly and fraud detection application could be a very good example there. Consider a credit card processing application. So the system should be able to detect fraudulent transaction within few milliseconds, and also it should be able to take a corrective measure within that period, something like blocking the card or triggering alarm or doing some kind of another action. So everything must happen within few milliseconds. So that's another use case. And then another applicability here would be inferencing a machine learning model. So in this case, the model has been deployed and has been trained. So what we do is we invoke this model to generate certain results, something like personalized recommendation. For example, if you build a online store, and when users go through that store, you get their clickstream data, right? You get their activity feed, and then we can analyze that activity feed with a machine learning model and generate a recommendation for next iteration. So that's another one. And then dynamic pricing, estimating ETAs for ride-hailing applications. So these are a few other example use cases for this category. And then if I bring in that preset equalizer here, so this is how the entire 5 slides would look like. So here the must-have properties would be high freshness of data. So the freshness of data must be in few seconds of time, because this is about making decisions. So we need to make sure that we are making decisions based on fresh data instead of stale data. And also ultra low latency should be a factor here, and others can be in moderate values. And then when it comes to technology choices, what kind of tools you can use to implement this kind of solution? So I would say the best would be stateful stream processors, because like Apache Flink and Beam and other kind of things, because they provide lots of abstraction over this kind of uh, uh, low latency and fault tolerant processing. Because if you consider Flink application, it provides this event time semantics, so that you can build event driven applications like anomaly detection pipelines. And then and these tools have closely related to machine learning applications as well. So there's a good combination you can build with that. All right. Second category, that's user-facing analytics applications. Traditionally, the access to analytics within an organization has been restricted to only a handful of user roles, something like C-suite executives or data analysts or data scientists. So they had the keys to analyze all your business data. But with the introductions of this data products concept, and then the SaaS platforms, lots of products or organizations started rolling out and giving access to analytics for their end users or customers. For example, uh, these users would see their activities or performance of their platform in a nicely laid out dashboard, in a visual dashboard with faster page loading times. So, for example, the best example I could give you is if you happen to own a smartwatch or a smart uh, application tracker or fitness tracker, the moment you open up the fitness tracking dashboard, you would see a user-facing dashboard. So that's the best example because uh, that's consumed by end users rather than few people within a particular organization. And then if you are a content creator like a YouTuber or blogger or someone, then you can see your channel performance or content performance in the these kind of a dashboard. So these are perfect examples for end user facing analytics application. And these applications have a significant property, that is the data they see in this dashboard is not the current state, it's aggregated view. So that's one significant feature. That means summarized view. So when we talk about the sliders, so this is how the preset template would look like. So there are 4 checkboxes. So ideally, the freshness of data also matter, should be high because it's going to be decision making by humans. And then latency should be low, and because if the latency is higher, we can't expect a good user experience from the dashboard because it's user facing, and sluggish dashboard will make the user experience really difficult. And then the support to complex queries, because like I said in the slide before, these queries project aggregated results. That means the underlying database should be able to do on the fly aggregations, slicing and dicing, and summarization. So this is where you need to have lots of support for multiple joins and running multiple aggregation queries. And also, another critical support you need to have here is the support for high query throughput, because this is exposed to your end users. That could be like maybe hundreds of thousands of people concurrently browsing a dashboard. Just think of your Apple smartwatch, or you open up the fitness dashboard and see your results after a run. And there can be like hundreds of thousands of concurrent users watching the same dashboard at the same time, and that will uh, spawn like say exactly same amount of queries to the underlying database. So high query throughput must be supported. So when it comes to implementation, uh, I think so. These are the best in the industry you can pick from. So ideally, real-time OLAP databases should be a good choice here. So because they provide support for streaming data ingestion, data freshness is preserved because these databases are able to ingest data as they are generated, and then a few seconds after it will be ready for querying. And also they have rich indexing support and columnar file format storage. So that means you get ultra low latency queries. Also, databases support multiple joins and running aggregation with low latency. That means you have the complex query support and high concurrency support as well. And that's about user facing. And then we have operational monitoring systems. So basically, these systems support humans to make decisions. So unlike the machines we saw in the first category, these are for humans. These are made for humans for assisted decision making. Basically, these systems are utilized by internal operations teams rather than end users or customers. So the roles could be like internal operational teams like SREs, DevOps, and network administrators. And also the usage pattern here is, so these databases can ingest incoming data, and then also this database is all most of the time coupled with a real-time dashboard, most of the time mounted in a central big monitor in a central operation center, projecting the current status of the world. Could be health status of a server cluster or something. And not only they can produce operational metrics, but they can also project business KPIs like how many orders you got within last 5 minutes and what's the failure rate of a API or something like that. For real-world examples, we can see infrastructure monitoring is a prime example here. So what you see here is a Grafana dashboard scraping from uh, time series data. So this is always good for monitoring and detecting what is going on of the health of the infrastructure. And then when it comes to IoT devices, IoT dashboard would be a really good example here, especially uh, projecting and performing operation on time series data, and then KPI dashboards as well. So when we talk about the templates here, it could be so what can be high must have. So freshness of data, it's a must here. So uh, because this is again decision making, so decisions are made by humans. So freshness of data also matters. So high fresh high freshness of data is expected. Latency also matters, but we don't need super latency. I mean, super ultra latency. It could be in milliseconds, but we can tolerate up to one or few single digit seconds latency here. Concurrency is low because this is not exposed to your end customers. So it's usually accessed by few operational team members, and so it could be concurrency would be really low at a time. Complexity of queries and historical data can be in moderate values. Especially historical data is required for some extent because when you are doing monitoring, you need to identify trends, right? I mean, in order to identify trends, you need to have the current status of the world as well as the uh, access to certain amount of historical data. You don't need to have the whole data set from the day one, but you need to have at least data for up to like few days back, because you can then only you can compare the current status of the world with the same value in the last week, and then you can identify a trend if these two values are two apart. So when it comes to technology choices, there are sorry, two choices you can present. So time series databases and full text search engines. When it comes to time series databases, Prometheus is always a good choice. And when you are dealing with IoT workloads on time series databases, InfluxDB is a good one, and Splunk. And then for full text search engines with indexing support and rich aggregation support, you can always count on OpenSearch and engines like Elasticsearch as well. And then finally, we have our final bucket called ad hoc querying on large data sets. So basically, this is where you have your whole data set, entire data set, and it's getting bigger, and you are ingesting streaming data into that data set. The requirement here is to run quick ad hoc queries on this data set with on-the-fly questions, and you need to get answers back in few minutes, but not in hours. If the query takes about more than hours, you should consult a batch processing engine. So this is kind of system we should use when we do some kind of experimentations of ever-growing set of data. So the volume of data is really high here. So it could be in the scale of petabytes or terabyte scale. And and also another specific thing is there's no defined query patterns like when you're doing monitoring or user-facing analytics. So if you're doing a if you're building a dashboard with no interactions, or even with interactions, you can define predefined query templates. Like, for example, when you project this pie chart, the underlying query should be like this. It should be static. But here, the shape of the query cannot be predetermined, and it's ad hoc. So because of this nature, use there are certain things this database has to sacrifice. We'll have a look at that in the next slide. But in terms of these databases, it's usually coupled with an interactive dashboard for users to provide interactive slicing, dicing, and drilling down on this data. If you are familiar with a Tableau-like interface, this is what I'm talking about. And for example, the audience of these kind of application can be twofold. So for example, the first category would be internal analytics people like data scientists, data analysts, and these kind of roles. So they have massive set of data set, and the data set is ever growing. All they need to do is run an ad hoc SQL query and get a BI dashboard or report generated. And then the second group of people would be operators. So this is where this use case differs from monitoring, because in monitoring you mostly uh, have projections in the monitoring, and you don't usually go there and drill down. But here in these cases you have the full length data set, and you can do some sort of drill down on this data to troubleshoot on a specific issue. For example, in this case, we can consider combine this this use case with the first machine generated use case. For example, let's say we are reading from an IoT sensor, and then that IoT sensor has detected an unusual temperature uh, in the last 5 minutes, and then it triggered an alarm, and then this alarm triggered, and there was an email sent to this SRE or the operator person, and then what this operator can do is can it needs to respond to this alarm. So what it does is it goes to this ad hoc querying, and it comb through this last hour data to determine what specific data point has caused this incident. So this is all. Sometimes it can be overlapping and interconnected. When we think about our preset templates, this is how it would like. So must-haves would be historical data and support for complex queries. We need to have a bigger picture, more amount of historical data, ideally from at least a few months worth of data to have a big picture of these queries, and also support for complex queries, because there can be multi-dimensional queries, and so because of that we need to have multiple joins between different tables. So the underlying database should support these kind of things. Concurrency is low because this is not going to be exposed to external audience. It will be handful of operators and uh, analytics people doing all the querying. And then latency can be within seconds if it is nice, and then we can tolerate up to few minutes. But if it takes more than 1 hour, it's not going to be good. Then we should switch to a batch processing engine. Freshness of data we can tolerate up to like few seconds or few minutes. So because this is most about experimentation, and a delay of few minutes in data can be tolerated. So when it comes to technology choices, so there are a couple of things we can consider, especially query engines like federated query engines like Presto, Trino, Athena kind of things. So what they are really good at is they can query different types of data stores at the same time. So you can combine both the historical data and the current state of the world at the same place, and you can determine trends and those kind of anomalies kind of things. Also, you can consider data lakehouse platforms like Databricks because they have the ingestion and also this historical data storage support as well. And then just wanted to highlight we have these streaming databases, a new concept in this data domain. So basically, streaming database is a hybrid between a stream process, stateful stream processor, and a database. So they have borrowed good part from both of these concepts, and especially these streaming databases can ingest uh, data from streaming data sources like Kafka and Redpanda, and also they provide the indexing. So uh, that is borrowed from databases. So the good part is these databases appears to play nicely on all the sliders. I mean, they tend to check all the boxes on these five properties we have discussed so far. But it's fairly new concept in these days, so we need to wait some time to get them mature over time. All right, let me recap what I have discussed so far. When you are presented with your next real-time analytics use case, use the five properties or characteristics as five sliders to assess your use case and assign different scores for these values. For example, you might have a internal facing application that doesn't need high query throughput and latency. In that case, you can weight those sliders accordingly. And then uh, if you do that a couple of times, you can choose the most appropriate real-time analytics technology for your next project. So it's, I mean, like I mentioned, there's no clear-cut way of separating that out. But if you're starting from scratch and if you have no uh, background in real-time analytics, these five sliders and four buckets will serve as a starting point for you. So it's okay, perfectly fine to have some overlapping between these use cases. So it should be treated by on case-by-case basis.